Now let's take a look at our first OS kernel, which is implemented in this t.c file. Recall that we defined the data structure proc, which controls the process information. So we declare two such instances. One is proc number 0, another one is the pointer. It's called running. It points at the currently running process. You may refer to this graph. Imagine this is the process number 0, and then this is the pointer. It points at the active or running process. Now inside the main, it has initialized a display. We can just utilize it. It's not part of this scheduling job. We point the proc pointer running to the first process, proc number 0. This ampersand sign just says, okay, you get the address, and then it's assigned to the pointer running. Then immediately the kernel calls the T switch, which is a task switch. It tries to switch the process to another one. We only have process number 0 in this very initial kernel, so it switches to itself. But let's see how the T switch works. So the T switch is again trying to carry out the job of context switch. This part should be done in the assembly instructions because we have to save context. The context being saved inside this T switch is the current context to have a save. We get all the general purpose registers R0 up to R12, and then also remember the link register. These are the necessary part for running process context switch. This should be familiar from the previous samples as well. Now the following part is to save the position of your stack pointer. Remember, each of our process is defined with its own stack, K stack. So the following code here is to reserve the stack pointer. We use the current pointer that is running. Actually, it's already pointing at our process number 0. So when we load it and then dereference it, we are actually pointing at the current process number 0. This offset 0 just means this is the beginning address of that process, and then it stores the stack pointer to this R1 offset by 4. Why this is the case? Because if you refer to the definition of the struct, actually the first element is an address. So it has 32 bits or 4 bytes. So you offset by these 4 bytes, you are pointing at the second element, which is the kernel stack pointer. That's why you see this offset by 4. So actually lines 23 up to 26 are all about saving the context of your running process. In our case, it's the process number 0. Then the T switch immediately tries to schedule the next process. It's defined in the kernel. So let's go back to t.c. It's here. You see inside this initial kernel schedule, it only has one process, that is process number 0. In other words, it just switched to itself. In the future, we'll see more processes running at the same time. We are going to switch to other processes, but this one just illustrates the concept. So scheduler does the job of switching to the next process. In our case, it is just itself, process number 0. Then we resume the context. So our R1 again points at the the pointer running, dereference it. You remember here, running, the pointer is assigned to process number 0 again. So running is actually standing for the process number 0. You load the address, beginning address of process number 0. You recover the stack pointer to your SP. It's just recover the stack pointer for this one. And you load other general purpose registers to their positions. So you have resumed a context. This is the key of the kernel scheduler. So in summary, the main only does two jobs. It creates a process and then switch. In our case, the switch happens to itself.